Just
What's the clicker?
just the right thing there. Right. So good morning, I'm Shimon Shapiro. I'm a doctoral researcher at Brunel University in London, and I'll be presenting today some work I've completed with my colleague Abin Matthew, our supervisor.
Speak up a bit louder or use the microphone, please.
Yeah,
Go for it.
so I'm ready.
It should be on.
Okay, hear me now? No? On. Testing.
Sound disappears in press.
Okay, is that better? Hear me? Okay, good. Okay, so I'm Shimon Shapiro. I'm a doctoral researcher at Brunel University, and I'll be presenting some work I've completed with my colleague Abin Matthew, our supervisor Professor Huazao, and PhD sponsors and a company that I do some part-time work with, Chris Smith and Kelly from Emissions Zero and the SPL Rail. So this work is on dual fuel ammonia engines for rail applications, and particularly for locomotives in this study. Not changing. Sorry. Okay, so owners and operators of internal combustion engine powered rolling stock under pressure to lower their carbon emissions, lower their exhaust emissions, and transition away from using fossil fuels. Compression ignition or Rudolph diesel engines, they're the prime mover of choice for self-powered rolling stock, having previously replaced steam engines, and those engines are more efficient than their spark ignition counterparts. Locomotives have a long service life, 40 years is typical, and in the UK, there are units up to 70 years old still in use. So owners and operators, they're keen if they can to evolve those assets rather than fully replace them. So what are dual fuel engines? So they use two fuels simultaneously. You displace in the process some of the diesel fuel. They retain the high efficiency compression ignition process. So that's high efficiency compared to spark ignition engines. You can evolve existing engines, or indeed you can apply it to new build engines. You can adapt lower carbon emission alternative fuels or renewable fuels in the diesel engine. Those fuels are typically otherwise used in spark ignition engines. So for example, compressed or liquefied natural gas. Difference there is how they're stored in the fuel tank. And there's a renewable counterpart for that of renewable biomethane. LPG and its renewable counterpart biopropane. Hydrogen, depending how you make it, blue, grey or green. Ammonia, which is this work. And then other fuels shown to date, there's methanol and ethanol dual fuel. So background to diesel engines just very quickly, those who may not be fully conversant with them. So 4-stroke cycle, inlet, take in charge of fresh air, compression stroke, the air is compressed, pressure and temperature rises, diesel is injected towards the end of the compression stroke, and then ignition occurs, power stroke drives the piston down, and exhaust stroke, final stroke, pushes the exhaust gases out. For a dual fuel engine, same again, inlet, we add an injector, an additional fuel system, and an injector for the inlet manifold for your second fuel. So you'll pull in your air and also your second fuel during the intake stroke, and then thereafter it's the same. The diesel ignition then ignites the second fuel as well. So what follows is the same. So just a little bit of quick background on previous projects with Devolution and Emissions Zero that this work has partnered. So they started doing dual fuel trucks. This is a diesel LPG truck. The fuel tank there, that silver rectangle, that's actually a replacement for the diesel tank. There's a smaller diesel tank and LPG cylinders alongside it under the cover. And later they did LNG dual fuel. That's a cryogenic liquefied natural gas tank. And later feasibility studies. So looking at rail, there was one for the 37 and for the 59 and the 66, which have different engines, but they're the same body shell. And those studies looked at diesel CNG, diesel LPG, diesel hydrogen, and the renewable fuels for CNG and LPG. This also led to some vehicle conversions. This is a Class 180. That's got a 19-litre horizontal engine in each carriage. That was converted to dual fuel diesel LNG. The engine was developed in a test cell, the dual fuel calibration, and a bespoke fuel tank was developed. There's 2 LNG tanks there and a T-shaped diesel tank in the place of the original diesel tank. The space is very limited on these, so that was a solution for these. And then later there was a Class 73-9. That's there's 2 73-9s types, both repowers, one by Brush, one by RVEL as was. So this is the RAM or the RVEL one. This has got 2 19-litre engines, similar to that in the Class 180, but common rail. So this was diesel and LPG. And here the additional fuel tanks were installed in a space near the roof in the equipment room in a gas-tight enclosure. So turning to this work, so this is a feasibility for the Class 37. One of our CAD models of the original form with 2 diesel fuel tanks underneath. So a quick review of the layout. So key things here, so there's a very large diesel engine pretty much in the middle, and then 2 fuel tanks. As built, they had 1 fuel tank and 1 water tank. For when these were replacing steam engines, they had a water heater on board for providing steam to the carriages, but later they got a second fuel tank. And that's a diagram of a refurbished one, pretty much the same. On the right side, some of the equipment's changed with the electrical rebuild, but the layout's very similar. So that's the English electric engine of the Class 37. That's around 180 litres, that engine. Large generator on the back. The later one's got an alternator. And then there's an inlet pipe running across the top of the engine, individual cylinder heads with the engine below, and that's a V12. So this work took a similar approach to the previous 37 dual fuel study. Key difference is that here we're looking at dual fueling the original engine. The earlier study actually looked at repowering the 37 and the 66 with new engines. Later, stage 5, common rail fuel systems. This is looking at the original engine. So relied on data that was from load bank testing to get a baseline and data from the original engine's fuel consumption and exhaust gas emissions. This engine has a notchless control. Power lever's got no steps, so you can have any power you want. There's no steps at all. So the data from the load bank, you proceed through a number of steps along the power curve. The data you get is the fuel consumption emissions versus the main generator output. But if you then correct for that main generator's efficiency, auxiliary load that is also being delivered by the engine, then you can read back and your data is then referencing fuel consumption and emissions to actual engine's total power output. We worked with a number of operators to get operational data, OTMR, for a number of routes, and then combining the load bank data mapping onto the OTMR data of your power over time, the lookup tables using your load bank data. Then you get fuel consumption and emissions totals for the routes as well as instantaneous as you go along. So here's this load bank testing a Class 37 on the network rails. That's the yellow colour, and that's at Loram in Derby. So for the dual fuel ammonia work, began with a literature review led by my colleague Abin, who unfortunately can't be with us today. That was looking at a number of studies, different engine types, but focusing on those that were comparable to that English electric engine. So single diesel injection event, main only event type approach, and the typical achievable ammonia to diesel ratios that you can get, and then using that data, mapping that again using the modified load bank data. Initial results for some routes so far. So the full data there, that's including all the idling that it does before it goes into service. The what's called section is just when it's actually on the route. So there's clearly an opportunity to address dual fueling at idle or reducing idling to improve that fuel consumption. For our later work, we'd like to look at if we can dual fuel at idle as well to improve that. And then turning to our modifications to the 37. So this is the original layout, 2 fuel tanks. So we replaced one of the fuel tanks with 2 large low pressure storage tanks for ammonia. The storage is very similar to LPG. So that's it's a 30 bar burst pressure tank, working pressure about 10 bar. And linking into some new work at Brunel, we've got a new ammonia fuel system to our test cells. This is the fuel supply outside the building, stainless steel lines into the building, and this fuel system's been developed by my colleague UKRRIN. And this is our single cylinder heavy duty 2-litre engine being used for the studies and the combustion work. And on the exhaust side, we've got a scrubber to remove ammonia from the exhaust before it vents at the top of the building. So the combustion work that we're developing here, we're looking at alternative combustion strategies to that which is typically been used with moving on from the single only, main only injection approach of the original engine, looking at multiple injection events and amending the timing, alternative combustion strategies, in order to then apply that later to that's on too far. So we'll apply that data that we get from the single cylinder engine, looking at alternative combustion modes, to then develop new data sets for a new engine for the Class 87 as a repower using ammonia and diesel dual fuel, with a higher proportion of ammonia being used than the initial studies to date. And this is an ongoing project, working with operators, getting more route data, more simulations, and continuing the combustion modelling work as well. Okay, thank you very much.
There's a bit of time for any questions if you have any.
Is there such a thing as green ammonia?
In process, yeah. So there are newer production routes coming for renewable ammonia, relying typically on renewable hydrogen as well in the process.
Any more questions?
I've got one. Are there any operational challenges that you have involving both storage and refueling of ammonia alongside the diesel?
Right. Yeah. So it's with the LNG and LPG locomotives we've done. We've put the fuel supply into key depots that they work at. With the DMU, it refuels every day, so that's relatively easy. The 739 works all over the country, so it's more restricted. But in all cases, they can revert and work on diesel only. So it's similar in a way to how diesel was rolled out. That original diesel locos were limited to certain routes and for the fuel rolled out. But with dual fuel compared to a dedicated spark ignition engine, you can just run on diesel if you have to. Whereas dedicated engines would be more stuck or limited when they couldn't refuel. Okay.
So up next we have Subcon talking about overhead line and catenary free systems.
Can you hear me all right? Okay.
It's probably better with the mic.
All right. Hi, good morning. Can you hear me all right? Okay, today I'm talking about feasibility study of alternative overhead line equipment for Sheffield to Manchester services. My name is Bagon Peter Ashai, PhD student at the University of Sheffield. So today's contents will cover the background research in the electrification in Sheffield, and then move on to the Sheffield to Manchester services, and we talk about options for electrifications and optimize simplified machinery. So key electrification research in Sheffield are here. It started like 10 years or more ago. Okay, so in the previous research, there is a dynamic modeling of the pantograph and catenary system, including the contact wire gradients and aerodynamics, and then arc damage assessment as well using the laboratory equipment. And in my research, I've been conducting a research in an alternative configuration of the catenary, and I consider dynamics of the system, geometric optimization, and combined damage assessment. So let's have a look at the problem today. Sheffield to Manchester services is quite important for people living in between these two cities. It starts from Sheffield train station going towards the Peak District. Really nice scenery, right? So it goes through Don and Tutley and then going towards Hope Valley. At this point, some trains will divert to Mill Central, going towards Manchester Piccadilly, and some trains will go towards Stockport and then Manchester Piccadilly, and then some will go towards London Street. In these services, there are three operators: Transport Express, the EMR, and Northern Rail. There are some freight trains as well, with the speed up to 90 miles per hour or 150 kilometers per hour, and with the frequency at more than 50 per day. It's very important for people living in Sheffield and Manchester. I know some people commuting every day as well from between these two cities. And interestingly, between these two cities, most services are diesel engine power. So in every journey, it produces emission. So because there is no electrification in between these two cities, so to improve these services, we have a few options available for us. So what are the options? We have got the full catenary, just like the main line, the high-speed 2 project, so, or the East Coast main line. And then we have got the trolley wire system, which is similar to tram, just like in Sheffield, Manchester, or Birmingham. We have got some simplified catenary, which we will see very shortly how it looks like, how it works, how it performs. And we've got some other options like battery, hydrogen fuel cell, bimode, and trimode, but these are not in my research area, so we will not talk about it today. Right, so what is the OLE? So basically, it is an infrastructure that is built along the track. It draws power from the power station through the contact wire here. Here, all right, and then the electrical energy will go through the contact point and then transfer current towards the pantograph mounted on top of the train. So it provides traction to the train, basically. But from mechanical engineering perspective, the most important system is in the circle, in the contact point, because it determines the performance of the system. So generally, the material just looks like this. It has supporting masts. You can see three of them in this picture. All right, and it has contact wire in contact with the pantograph, and there's a little train there. All right, so there is a catenary wire, or some countries may refer it as a messenger wire, to provide support to the contact wire along the span through the vertical droppers. So it's quite, you can see a lot of components here, right? But typically there are some other configurations as well. So let's say the most simple form of OLE is a single wire, just a cable, just like a tram, and then it is suspended at the mast, and there's no support between the spans, so it's quite flexible, and then quite bouncy as well. So it's good for low speed application, but for higher speed, you can see some variations of catenary, like the stitch and compact catenary as well. So they are rigid. You can see a lot more components between the span, so it allows higher operation. But what is the simplified catenary? So we talk about managed sensor services. It requires 150 km/h speed, right? We have something not too good, right? Just too flexible for low speed. We have something too complicated, too good for this application. So the idea of the simplified catenary is to get something in between for the not too low and not too high speed. Right, so how does it look like then? So basically, it's based on a single cable, and then we add the components to support. So you can see the stitch wires in black, and then the red color is the flexible support, okay? The stitch wire can be placed at up to 7.5 meters from the mast. So let's say some designs I have analyzed, you can see different position, different numbers of stitch wires and different configuration as well, different properties. So yeah, we got crazy designs, a lot of them, with a lot of like computational energy. So, but how do we assess? How do we know if they are okay, if they're not okay? So, sorry. So assessment started with the finite element model I created based on the previous work done by Mr. Sam, Dr. And I validated this model using the test track data, and after that, I performed a geometric optimization using the surrogate optimization algorithm. In the optimization, we consider a few different objectives. So firstly, and most importantly, the dynamic performance. So it's about the behavior of the interaction between the pantograph and the contact wire. And we also consider fatigue and tensile failure as well. And lastly, and quite important, we consider wear in this assessment in conjunction with laboratory assessment. There's some gap, you can see an empty area, right? That is a future work, because to complete or to extend this analysis, we may need to extend it to cover the side winds and aerodynamic impacts on the overhead line. And also, operation with multiple pantographs can be important as well. And the contact wire gradient. So how does it look like? In this image, the top image is the benchmark catenary with 5 droppers. And with the same scale, we can see the optimized simplified catenary at the bottom. There are 3 stitch wires at 4 meter, 4 meter, 7.1 meters, 7.4 meter with a stiffness of 1,400 something. Right, so you can see it's a lot more simple than the conventional catenary with a lot fewer components. Yeah, but how do I know it's working? So we assess the performance. The most important thing is the contact force, which is the reaction force between the pantograph and the contact wire. So in this graph, we have the position in the horizontal axis and the contact force in the vertical axis. And we have 2 cases. The red color is the benchmark catenary. Ideally, we want the contact force across the span to be constant. That's ideal condition, and then that never happened. So the benchmark catenary shows some variation in contact force across the span, but it's quite close to being constant already. That's very good. Alright, so there's no problem with the catenary. But for the simplified catenary, you can see in the purple color, it shows some more variation in contact force compared to the catenary, which is quite not far off, right? But there's some weaknesses, well, which we'll talk about it later on. So we got contact force being close to the criteria, but I can't just say it's going to work. You need to comply with something. So the compliance was done with the standard EN 50367, which requires the standard deviation of the contact force divided by the mean contact force to be below 0.3. And in this picture, we have the train speed ranging from 60 to 300 kilometers per hour on the horizontal axis. And in the vertical axis, we have the standard deviation divided by the mean contact force, and then we have an acceptance limit at 0.3. So anything below 0.3 is accepted and is working safely. So you can see the category, it is under the 0.3 limit from the low speed to high speed. So it's working fine. Like for the freight, for high speed, like the LNER Assumer or the Sheffield to Manchester at 150. But when you consider the simplified criteria, it's working okay until 150 kilometers per hour. You see, it just get close to acceptance limit. So from this analysis, it means theoretically it should work in the Sheffield Manchester services. All right. So is there any other consideration? Yes, safety. So you can see this is the configuration with 3 stitch wires. The blue color is the contact wire. All right. And then there are 3 stitch wire, one at 4 meters and one at 7.1 and 7.4 meters away from the mast. You can see the change in gradients in the contact wire at the outer stitch wire. That can cause stress concentration and can cause higher stress and risk of failure as well. So from our analysis, we got the static mean stress to be 166 megapascal, which is well below the yield strength and the ultimate tensile strength. So we can just say you will not fail by static load. But what about fatigue? Commonly, we quantify fatigue in OLE using the equivalent stress, which is a function of static mean stress, alternating stress, and strain amplitude. So the previous research in Sheffield has discovered endurance limits, which provides infinite life for the contact wire to be 150 megapascal. From my analysis, we found this cyclic loading to be 50 megapascal. So you can just say it may not fail by fatigue. Right. So yeah, back to this image. I was talking about weaknesses of the system just now, right? So let's take a look at it closely. So at A and B, at A, we have a contact force spike from around 100 up to 160, a big jump, right? And then this one can cause excessive wear as well. And then we have B, that is where the contact force approaching its minimum, and then in certain working conditions, it can reach 0 or below 0. When it reaches 0, that means the contact between the pantograph and the contact wire is broken. The contact loss is not desirable, we don't want it, but we can't sometimes prevent it. Okay, so what happens when the contact is broken? So in this video, I wanted you to see in the red circle, can you see it sparking? It's not really clear, I took it with my phone right behind the train station in Sheffield, so it's not really clear. But that behavior is not nice, it caused a reduction in hardness and a lot of subsequent problems. We replicated that behavior in our laboratory. In the middle, you see it in the middle video. We simulated this behavior in our laboratory to assess how much damage it will cause to the contact wire if arcing occurs. So from our analysis, it depends on the severity of arcing and number of arcing, but generally it produces a lot of contact wire wear when arcing occurs. However, it's in my time limit, I can't just integrate this back to the model to complete the analysis. So this is a future work again. Right, so let's talk about money. In terms of investment, let's see how much the simplified material can save. Yeah, when we use the conventional system, right, we need the droppers and the messenger wires, which requires a lot of materials. But if we use the simplified material, we can save the materials for droppers and for the messenger wires. But we may need to invest more in the foundation, right? But in terms of maintenance, with fewer components, obviously it requires less maintenance. Okay, right. So the last bit, challenges in this system, if you want to put it forward to Sheffield to Manchester services, we know it can work from the analysis, but what are challenges in practice? Bridges and tunnels are around this Peak District, and especially the Totley Tunnel, which is 5.7 kilometer long. And to build the contact wire to enter the tunnel, it requires the contact wire to lower its gradient gradually towards the tunnel. But it was found in Sheffield, like in the previous research by Dr. Hayes, that the gradient may not cause a problem, but that was done with the conventional material. So this aspect requires more work as well. So in conclusion, we have seen options for upgrading the Sheffield to Manchester services, and we have seen a series of analysis to see how it works, how it performs. And we have seen future research opportunity as well. And in conclusion, from my biased opinion, it can work. Right, thank you. Yes, please.
I'm sorry, it's always me. Can you go back to slide 15, please?
15. Yes.
That's the one. At the 100 kilometers per hour, you have got an exceedance. Now, the train has to go through that speed if it stops anywhere. How do you deal with this?
At 100 kilometers per hour. So
If you go to 100 kilometers per hour, then you get above 0.3.
right. So
Because your train actually will have to be able to stop in Grindleford.
yeah. So obviously the train does not run at 150 all the time. Okay. So the 0.3 is like a mythic number that is used in the catenary, the full catenary. It has the reason behind it, but we have conducted a deeper assessment and then we found that it can work at 100 kilometers as well. So we need, at some point, if this is used in the future, we need to define a new number for this simplified system rather than using the 0.3.
Thank you.
Thank you. Yes.
So I have a question. So have you done any modelling around kind of failure of your straining wires and the likelihood of that causing failure wire? So we get lots of problems with things like that. I guess there's two parts to that. One is a proper failure in itself loses an element of support in the system. But the second being those droppers are generally distanced to a point where if they fail on the top or from the bottom, then they won't hang down. But because yours are all over a length that's greater than the vertical distance, all of them would then become an obstruction upon failure of the pantograph.
I'm doing that with, former employee of Network Rail. I've been doing this research with him actually, but the paper is not finished yet.
Yeah.
So it's not specifically for my system, but it was for the general conventional activity. So we found that when the dropper is missing or removed, it increases the contact force and it can lead to failure in the 1,000 droppers. So we have done this.
But this was more obviously if one of yours fails, whether it failed at the top joint or the bottom joint. By the time it's swung down, it's going to be foul of the contact.
Yes, I have not done that with my model, but I've done something similar in similar system.
Okay.
Thank you. That will be a future work. Thank you. Yes, please.
In your earlier animated shot where you showed the iterations through your design process,
Yes.
can I ask, when you were designing each of those iterations, is the process that the first design, if that fails, it informs the second automatically, or are you independently defining each of those designs and then checking sequentially?
It's generally there's no failure in those designs because somewhere is performing better than the other ones. So we employed the rocket optimization algorithm, which is a gradient-based algorithm, optimization algorithm. So the previous iterations will inform the future iterations to get a better, hopefully better design. So that's the process of optimization. Yeah, to answer your question, yeah, it was considered.
Thank you.
Thank you.
Thank you. Thank you.
Right, so just to keep this fresh, the next speaker is going to be online, so just bear with me. So I stop presenting. So Ibrahim, you should be able to share your slides.
Yep.
And hopefully I'll get enough sound.
Is it visible now?
It is indeed. I don't know if
Can everyone hear?
Yeah, I'll try and make it as loud as possible in the room, but
Okay.
can I make that any bigger? Okay, right, I think that's as good as it'll be, so yeah, crack on.
Okay, I hope my voice is clear and everyone can hear me. Good morning, everyone. My name is Ibrahim Al-Hashimi, PhD student in Brunel University, London. Today, I will present my research on the design and dynamic energy management strategy for an integrated fuel cell gaseous state hydrogen storage system for locomotive applications. This project will explore the innovation of reducing the emissions in railway transport using hydrogen fuel cell. At the beginning, I will cover the motivation of hydrogen for locomotive applications, the challenges of electrification, and also I will present the PEM fuel cell system. We will review technical specifications and the energy management approach, the cost analysis, and I will conclude with financial projections and final insights. Yeah, for the why there's a necessity for the hydrogen trains. During the last decade, we can see like the climate change became one of the greatest issues in the world. The increase of dependency on fossil fuel, the carbon emissions become one of the main global warming reasons. So we can see in the lowest graph that the increase of the price of the kilowatt hour of the electricity. So that's mean hydrogen power locomotives will offer a free, a zero emission, let's say, solution, reduce the noise in locomotive, and lower the operational impact compared with diesel. As you know, hydrogen fuel is clean, efficient, and a promising alternative to fossil fuel. It's ideal for reducing climate change impacts to go towards a clean solution like hydrogen fuel cells. So the cost of electrification, it's being calculated for one single truck kilometers to be 2.8 million pound. As you can see in this map, only the colorful routes are electrified, whereas the other routes still depending on diesel trains. What I did, I choose this specific route between Oxford and Worcester because this route is not planned to be electrified in the plan of the next years. So what I did in that study, I calculate how many stops in that route. Also, on Google Map, I calculate the distance of that route, the speed as well. I used an app called Signal Box for that. So I choose a live train going from Oxford to Worcester, and I calculate the speed through that app. So also, only in 2021, the total consumption of diesel in locomotive sector was around 507 million liters of diesel. And taking in consideration the price of the diesel, so that's mean only on that year the consumption the annual cost of fuel consumption was around 1 billion pounds. So now, why hydrogen fuel? It will give zero emission at the point of use, free of noise and vibration. It can be retrofitting, and also will give some health benefit, environmental impacts. Comparing the hydrogen fuel with railway electrification, the electrification will be higher capital cost and also lack of flexibility, and will be like free of power interruption and other complexity of different standards. So for the proposed fuel cell train system, what I proposed in that system, I proposed a fuel cell train that will use hydrogen produced on site. I did choose Oxford Station to be like the hydrogen production station will be there, and we will use the solar power to power the PEM fuel electrolyzer to produce the hydrogen from green energy, with the aid, of course, of the grid, because we don't have like enough area to produce the required energy. So that's mean we will use combination between the grid and the solar power. This approach will reduce the carbon footprint and will supply the fuel directly in the station, so that will increase the performance of the work. So what I did the assessment on the current trains used in that route between Oxford and Worcester. They are using the Class 800. The railway operator is Great Western Railway. The route length was 91.57 kilometers. I calculate the speed, as I said previously, through the Signal Box app, and the UIC classification of that train was 22 Bobo 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 22, as it's shown in that graph below. The average speed have been calculated to be 70.2 kilometer per hour, and the journey duration was 1.42 hours. So the data collected, the speed on each station, I generate that graph depending on the speed that I got from Signal Box. So as it says, starting from Oxford until Worcester station at the end. So the proposed system of the hydrogen fuel cell will be depending on a fuel cell fitted on the roof. It's something like the Alstom hybrid I-lined train. So I will try to convert the Class 800 to have hydrogenic HD30 fuel cells, PEM fuel cells. We will have around 200 kilowatts of fuel cells in each car. So that will give us a power of around 2,712 kilowatts. We will need 3 assemblies of that. So because the first and last car will have like non-driving axles. So we will put the fuel cell assemblies in the middle 3 cars. For the hydrogen storage, the hydrogen will be stored on board. We will, in my study, the hydrogen required for 2 journeys will be 250 kilogram of hydrogen, and the pressure required 350 bars. And I choose for the hydrogen storage a carbon fiber composite, and it will be fitted in the roof. For the PV solar panels, I used Pylon PV software. So the number of panels on Oxfordshire, I will use even the car park to have solar panels there. So I will have a net power of 142 kilowatts, and annually it will produce 259,515 kilowatt hour. For the electrolyzer, I will use HTEC system electrolyzers that will produce 550 kilogram of hydrogen per day, and the energy consumption for that electrolyzer is 53 kilowatt hour per kilogram, with high efficiency around 75%. The annual expenditure of the electrolyzer, we will need around 2.8. This is the capital cost of the grid energy required per year. It will be around 28 million. And for the, whereas the PV will save around, 289,000 and 88,000 from the electrolyzer. On the right side, the annual energy required for the electrolyzer will be 8,500, 8,500,000 of energy per year will be needed from the grid, whereas the solar will produce not that much of energy. The good thing about this model, it can be applied in any other places in the world. So let's say if you are applying that in Saudi Arabia or anywhere with high solar radiance, this figure will be much better. The stationary storage, I propose to have like a 3 variable size range of 14.5 kilogram to 19 kilogram of hydrogen single cylinders, and it will be used based on the hydrogen needs in the stations. For the batteries in my system, I suggest to use batteries as well in addition to the fuel cell. So one set of batteries, I choose Axel battery with energy of 36.8 kilowatt hour. The continuous power of that battery will be 225 kilowatt. I also integrated a supercapacitor because the supercapacitor will give me the first push of the motor to give me the speed from 0 to 10 kilometer per hour. So I used scale mode supercapacitor with 162 volt and 92 farad. For the setup of the system, I had like different setups. One was only hydrogen powered locomotive. The second one was only battery powered locomotive. The third one was a hybrid locomotive using a fuel cell and battery. In that model, we just need one set of battery, and the hydrogen, as you can see, the hydrogen fuel consumption will be less compared with 129. It become 114 kilogram of hydrogen. But the last setup using the supercapacitor will give the durability and increase the performance of the whole system. It's clear now from the drive cycle between each station. The dotted red line is the supercapacitor push to 10 kilometer per hour. So I choose 80 kilometer per hour as like the top speed of the train based on the readings that I got from signal box. So taking that in my consideration, I did COPEX, OPEX studies. As you know, using a diesel engine for the class 800 will produce lots of carbon emissions. So I took in my consideration the carbon capture if I want to make the route clean of carbon emissions. So we will spend at the beginning the capital cost of the fuel cell and for the electrolyzer. But at the end, if we take in our consideration the payback for the carbon capture and the electricity produced and the fuel that we saved, we will have a reasonable annual return. So I did the annual return of the whole system. So as you can see in the first year, because we have lots of capital cost in the first year, but the second year we will have good saving and so on in the next a couple of years. So that the system will pay for itself with time. So to conclude, the research that I did, the research was exploring the case study that focusing on changing the traditional locomotive that's work on diesel engines into hydrogen hybrid model, and also the financial perspective and the capital and operational expenditure analysis demonstrate that the hydrogen hybrid train not only recover itself but also generate profit. So thank you for zero emission design and the carbon capture elimination will not be required anymore with that model. I'm free for any questions if you have any questions. Thank you.
Yeah, I don't think there's any questions in the room, and I think we do need to move on with time. But thank you, and thank you for coming online despite
Thank you.